Alright, we're continuing section 2.5, which is talking about continuity. And so just to reiterate what that is, definition. F is continuous at x equals a, the point, if the limit as x approaches a of f of x equals f of a. And again, that means two things, or three things. The limit exists, f of a exists, and the two things are the same. Okay, so what we're doing now is we want to take a look and see if where this example function is continuous and where it may not be continuous. Now again, if it's not continuous, one of the three things must not be true, right? So a graph like this, or a function like this, might be best to just kind of take a look at the graph. Boy, my chair is really squeaking. Let's take a look. So go piece by piece, and the function is being cut here at x equals 1 and at x equals e. So that's 1, and this is e. And this is just to remind myself that the function is cut there. So in this part of the graph we have x squared, and in this part we have natural log of x plus 1, and in this part we have x. Okay, now if we want to graph this piece, it's just a parabola. And so where will the parabola end up over here? Looks like the parabola is going to end up at x equals 1 here. Right? And because that's not an equal sign there, I'll leave the circle open for now. Okay? Next one, natural log of x plus 1. So just as a reminder, what does the natural log of x look like? If this is 0.1, then the graph looks something like that. So that's the natural log of x. So what happens when you add 1? Well, this graph just shifts up 1 unit, right? And so this is the piece of the graph that's going to fit into this middle piece here. And so you'll notice that at 1, what's the output? If x equals 1, natural log of 1 plus 1 is equal to 0 plus 1, because the natural log of 1 is 0. So that gives me a 1. And so that's going to be a solid dot on this side. So I'm going to go ahead and fill that in. And then this piece of the natural log will go right in here. Okay, and then it's an open circle here. And in fact, what is the value of that open circle? In other words, at this circle, let's see, at x equals e, our function is the natural log of e plus 1, and that is 1 plus 1, which would be 2. Okay, so this open circle then is at 2. Good, and then finally the graph of x is on the outside, and if we're starting at e, then the graph is going to start at e, right? And it'll be a solid dot at e, and then it'll be a straight line at a 45-degree angle, right, going up. Good, there's our function. Now, can you tell where the function is going to be continuous? Is the function continuous at points less than 1? Yes, because it's just x squared. And the polynomials, remember, this statement is true for all polynomials, right? And similarly, in this region, right, this is just the natural log, which is a nice solid function, and so the function is continuous here, and then similarly the function will be continuous there. So the only questions really are at the breakpoints, x equals 1 and x equal e. So let's be formal about that, because visually I think you can see, right, what happens at x equals 1. At x equals 1, you see that there's no problem there, but that's an intuitive idea. So what is the limit as x approaches 1 of f of x? How would I compute it? Well, it depends on whether you're coming in from the left or the right. So if I were to take the limit as x approaches 1 from the left, I would be taking x squared as my limit, and so that limit would be 1. And then if I take the limit as x approaches 1 from the right, I would be taking the function natural log of x plus 1, which is 0 plus 1, right, which is 1. Good, so the limit overall exists, and the limit is equal to 1. Okay, and then finally, what is f of 1? F of 1 is equal to, use this formula says to use this version, so that's natural log of 1 plus 1, which is 0 plus 1 equals 1. So in this case, we checked by definition that the function was continuous at x equals 1. Good. Now if you already see a picture, right, you already know it's going to fail for the continuity if it's going to fail. So what's going to happen at x equals e? At x equal e, you see that the limit will not exist. And why will the limit not exist? Let's go ahead and maybe move this way. So now the limit as x approaches e from the left of f of x is the natural log of x plus 1. And so that's the natural log of e plus 1, which is 1 plus 1, which is e. And if I want to take the limit as x approaches e from the right, which function do I use? I use x, and that's e, right? So the limit is 1 plus 1 equal to e? I don't think so. 1 plus 1 is equal to 2. There we go. And of course, now we see e is not equal to 2. So the limit at x equals e does not exist. Okay, therefore the function fails to be continuous there. Good. All right. Similarly, we could do another one. How about f of x equals x squared minus x minus 2 divided by x minus 2 if x is not equal to 2, and then 1 if x equals 2. Alright, so we want to see if f is continuous everywhere. Okay, and you see that really the only problem spot is going to be at x equals 2, because if you look at the numerator is, let's see, x minus 2 times something. What's that going to be? Looks like x plus 1, huh? Is that right? Double check that. I think that's true. And so therefore the x minus 2's cancel, and so what you're really looking at then, you could really say is this is x plus 1 if x is not equal to 2, and 1 if x equals 2. So what does that look like geometrically? The line y equals x plus 1 goes through the y-intercept 1 and a slope of 1, so that's going to look like this line here, except at the point 2, right? Because at 2 our definition changes. So let's see, let's put an open circle there, and we're saying the function is equal to 1 there. Good. So is this function continuous? Not continuous. Does the limit exist? The limit exists. Does f of 2 exist? Yes. But the problem is these are not the same. Good. So therefore this function fails to be continuous at x equals 2. And you'll notice that it is continuous everywhere else because it's just the function x plus 1. Good. Now, just to formalize that a little bit, let's write down a few theorems and then we'll do more examples. So theorems to help us compute. Theorems. Theorem 7, these are not in order from the book. This is the book number. This says that all the following are continuous on their respective domains. Okay, so that is all polynomials. all rational functions. And remember what a rational function is from our limits. Rational function is polynomial divided by polynomial. All root functions. All trig functions. All inverse trig functions. All exponentials. All logs. Have we covered everything? I think we've probably covered everything that you're familiar with. Theorem 4 is going to say that if f and g are continuous on domain D, so is, let's just list them all together maybe. So is f plus or minus g, so that's two of them, f times g, and f divided by g. And this one you got to make sure what? G of x is not equal to 0, right? And finally, theorem 9 says that if f and g are continuous on their respective domains, then you have to be a little bit more careful on this one. We'll see an example of that. F composed with g of x. The composition of continuous functions is also continuous. Okay, so that one's a little bit more tricky. We're going to go through and use these theorems now in order to prove that different things are continuous. All right, see you there.